And now in this lecture we'll find out the radius of the big circle. In the drawing we have a big triangle. Inside the big triangle we have two circles and a square. Note that the radius of this circle is equal to 1 unit, and one side of the square is equal to 3 units, and our mission is to find out the radius of the big circle. So here we will define the radius of the small circle as O. We define the point of tendency of this small circle with this side as D. We know that OD, point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of the circle that is equal to 1 unit. And here the radius OD is 1 to the point of tendency. Therefore, according to rule number 1, the tangent to a circle is perpendicular to the radius drawn to its point of tendency. This angle equals 90 degrees, and this angle equals also to 90 degrees. We also know that one side of the square is equal to 3 units. We define the vertex here as point A. We define this vertex of the triangle as point B. We define the vertex here of the triangle as point C. We will define this point, the touching point of the square with the triangle, as point E. We will define the touching point of the square with side AC of the triangle as F. We will define the touching point of the square with the circle as point G, and we will define the touching point of the square and side BC of the triangle as H. We will define the center of the big circle as point P. We will define the point of tendency of tangent BC with the big circle as Q. So here we have the radius PQ that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. You know that all the angles inside the square are right angles, so this angle equals to 90 degrees. This angle, it is also equals to 90 degrees. This angle equals to 90 degrees, and this angle, it is also equal to 90 degrees. So here we have also rule number 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So if you focus on the upper side of side BC, that is a straight line. So if you focus on the upper side of side BC at point H, the sum of the angles must be equal to 180 degrees. So this angle equals to 90 degrees. Therefore, the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on the upper side of BC at point H to 180 degrees. This angle must be equal to 90 degrees. Likewise, we have, if we focus on the upper side of the straight line BC at point E, the sum of the angles must be equal to 180 degrees. This angle equals to 90 degrees, so this angle must be equal to 90 degrees, according to rule number 3. Okay, so here we will define the touching point of the circle with the square is point K. We'll join points O and K together by a straight line. point O is the center of the circle. Point K is the point of the circle itself. Therefore, OK is the radius of the circle that is equal, of the small circle that is equal to 1 unit, of course. And we have the radius OK that is drawn to the point of tendency, that is to say, it is drawn to point K, that is the point of tendency of tangent FE with this small circle. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. So inside quadrilateral EDKO, inside the small quadrilateral, we have 1, 2 free right angles. Again, inside quadrilateral KOED, we have 1, 2 free right angles. Therefore, the fourth angle must be also equal to 90 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, therefore this angle must be equal to 90 degrees. So actually quadrilateral KOED has 4 right angles, therefore quadrilateral KOED is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say OD equals to KE. So OD equals to KE and OD equals to 1, therefore KE will be also equal to 1. Likewise, according to the same rule, KO equals to ED. But KO equals to 1, therefore ED will be also equal to 1. So actually we found out that quadrilateral KOED is not a rectangle but a square. Okay. So here, in the next step, I will present to you rule number 2. According to rule number 2, the lengths of two tangents from common external point to a circle are equal. So we have here the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. We can actually implement rule number 2 in our drawing, because here in our drawing, if we focus at the common external point, point F, from the common external point, point F, we have two tangents to this circle, tangent FK, and here we define this point as point S. So from the common external point, point F, we have two tangents to this circle, tangent FK and tangent FS. And according to rule number 2, KF equals to FS. So here, what is the value of KF? We know that FE equals to 3 units because it is one side of square of this square. So FE equals to 3 units and KE equals to 1 unit. Therefore, KF will be equal to 3 minus 1, that is 2. And according to rule number 2, KF equals to FS. But FK equals to 2, therefore FS will be also equal to 2, because they are equal to each other according to rule number 2. Now we will focus on the common external point, point C. From the common external point, point C, we have tangent CS, and we also have tangent CD. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, CS equals to CD. So if we define CS as X, then CD will be also equal to X because of the fact that they are equal to each other according to rule number 2. Okay, so in the next step, we'll focus on the right triangle, right three triangle, triangle EFC. in the right green triangle, triangle EFC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is EC, therefore the square of the hypotenuse is FC. Therefore, the square of the hypotenuse is FC squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to FE squared plus EC squared. I'll repeat again. In the right green triangle, triangle EFC, according to the Pythagoras theorem, FC squared equals to FE squared plus EC squared. Okay. So here the hypotenuse FC is equal to 2 plus x, therefore the square of the hypotenuse is 2 plus x squared, and it is equal to FE squared. FE equals to 2 plus 1, that is 3, so FE squared is 3 squared, that is 9, plus EC squared. EC equals to 1 plus x, therefore EC squared is 1 plus x squared. So in conclusion, we found out that according to equation number 1, 2 plus x squared equals to 9 plus 1 plus x squared. We'll open the brackets on both sides of this equation, equation number 1, and we'll get that according to equation number 1, two plus x squared equals to 2 squared, that is 4, plus x squared plus 2 times 2x is 4x, and it is equal to 9 plus 1 plus x squared equals to 1 squared, that is 1, plus x squared plus 2x. So here we have x squared on both sides of the equation, so x squared will get cancelled. So what is left from equation number 1 after we cancel x squared? In this side of the equation we have 4 plus 4x, and it is equal to 9 plus 1 is 10 plus 2x. Here we subtract 4 from this equation, equation number 1, and we get that according to equation number 1, 4x equals to 10 minus 4 is 6 plus 2x. So here we subtract 2x from this equation, equation number 1, and we get that according to equation number 1, 2x minus 4x minus 2x is 2x, that is equal to 6. Here we divide this equation, equation number 1 by 2, and we get that according to equation number 1, x equals to 6 over 2 is 3. So x equals to 3 units. So we write it down that x is equal to 3 units. X equals to 3 units. And then also x equals to 3 units. Okay. In the next step, we'll join point C and O together by a straight line. We'll join points O and S together by a straight line. Point O is the center of the circle. Point S is the point of the circle itself, therefore OS is the radius of the small circle that is equal to 1. So here we'll prove that those two white green triangles can go into each other according to side rule. So I write it down. We'll prove that the green triangle DOC, is congruent to this green triangle OCS. So why those two triangles can go into each other? First of all, DO equals to OS, and they are both the radii of the circle that is equal to 1 unit. In addition, we have CD is equal to CS, and they are both equal to 3 units, therefore they are equal to each other according to rule number 2. And finally, we have side OC is the common side that belongs to both triangles, so OC equals to itself, OC equals to OC, it is a common side that belongs to both triangles. Okay. So in conclusion, we found out that the two green line triangles can go into each other according to side rules. So I write it down. Triangle DOC congruent to triangle OCS according to side rule. Okay. And from the fact that those two right triangles can go into each other, we conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles must be also equal to each other. So if we define one angle as theta, then the other angle must be also equal to theta because of the fact that they are equal to each other. Okay. In the next step, we will define the touching point of side AC of the triangle and the circle as point G, as point N. We join points P and N together by a straight line. So here, point P is the center of the circle, point N is the point of the circle itself, therefore Pn is the radius of the circle that is equal to capital R. We join point C and P together by a straight line. But here, before that, we have here, we join here points S and D together by a straight line. So actually OC is angle bisector of angle C. I write it down. OC is angle bisector of angle C in triangle SDC. I'll repeat again. OC is angle bisector of angle C in triangle SDC. Actually, it bisects angle C into two halves. Each half equals to theta. Okay. Now we will prove that the big right triangle and triangle NPC, here, this angle equals to 90 degrees according to rule number 1. So we'll prove that the big right triangle PNC is congruent to the big right triangle PQC, this triangle. Actually, they congruent to each other according to side rule, and we'll prove it now. Here, side PN is equal to side PQ, and they are both the radii of the circle, therefore are equal to each other. In addition, here, if we focus on the common external point C, from the common external point C, we have two tangents to this big circle, tangent CQ and tangent CN. And according to rule number 2, CN equals to CQ. Again, CN is equal to CQ. According to rule number 2. And finally, side PC is the common side that belongs to both triangles, so PC is equal to PC. It's the common side that belongs to both triangles. Okay. So we actually proved that triangle P and C is congruent to triangle Q and D. Triangle PNC is converted to triangle PQC according to side rule. Okay. I'll write it down. Triangle PNC is converted to triangle PQC according to side rule. And for the fact that those two triangles converge to each other, we derive that those two angles are equal to each other according to the rule that corresponding angles in convergent triangles are equal to each other. So if one angle is equal to theta, then the other angle must be also equal to theta. So we join points P and Q together, points N and Q together by a straight line. Here we created triangle Q and C. We actually found out that PC is angle bisector of angle C. I will write it down. PC is angle bisector of angle C in triangle MQC. I repeat again, we actually found out that PC is angle bisector of angle C in triangle MQC. Therefore, we actually found out that angle C is two angle bisector, PC and CO. Okay. So, in the next step, we'll prove that the angle bisector CO passes through point P. I repeat again, we'll prove that the angle bisector CO passes through point P, or in other words, point C, O, and P, they are all located on the same straight line. Okay, so I write it down. We'll prove. So our claim is that CO passes through point P. So I already mentioned before, I can also say that our claim is points C, O, and P, they are all located on the same straight line. Okay, I repeat again, we'll prove our claim is angle CO passes through point P. Okay. So we'll prove the claim in a negative way. So let's assume that CO doesn't pass doesn't pass for point P. I repeat again, our claim is that CO passes for point P, and we'll prove it in a negative way by assuming that CO doesn't pass for point P. So if CO doesn't pass for point P, therefore we have here angle DCO. This angle DCO is equal to theta. Repeat again, angle, according to what we already found out, angle DCO equals to theta, while this angle PCB, what is the size of angle PCB? Here, BC, actually DC is part of BC. Again, DC is part of BC. Therefore, because of the fact that DC is part of BC, we can say that this leg of the angle are a common leg because they are both on the same straight line. So those two angles, they have a common leg, DC and BC. Okay, while the other leg of the two angles are OC and PC. Okay, we have here the leg OC and the leg PC. But according to our assumption, CP, COP are not located on the same straight line. If COP are not located on the same straight line, it means that angle OCD that is equal to theta will not be equal to angle PCE because they have actually a common leg. CD and BC are a common leg, while the second leg of those two angles, they are not located on the same straight line. Therefore, the second leg is different leg. And when you have one leg of an angle that is a common leg, and the other leg is a different leg, it means that the two angles can never be equal to each other. Here, OC is not on the straight line of PC. And here we have a common leg, therefore angle PCB can never be equal to theta, so we'll define angle PBC as alpha. Okay. So we actually found out that we have here two angle bisectors of angle C, and those two angle bisectors of angle C are not bisecting angle C into the same halves. Here, angle bisector CO bisects angle C into two halves that are theta and theta, while angle bisector CP or PC bisects angle C into other two halves that are alpha and alpha. Okay, repeat again. Angle bisector CO bisects angle C into two halves that each half equals to theta, while angle bisector to the same angle C bisects angle C into other two halves that are alpha and alpha. And this is impossible. Why it is impossible? For example, if angle C is equal to 30 degrees, any angle bisector of angle C will bisect angle C into two halves that each half equals to 50 degrees. Okay, so angle C cannot have two different halves of itself, because here, if angle C equals to 50 degrees, the only two halves that angle C can be bisected to is to 15 and 15, and that's all, not to any other halves. Okay, therefore, so due to the contradiction, that caused by our assumption that OC doesn't pass from point P, we conclude that our assumption is not correct, and we conclude that OC indeed passes for point P. Okay, and that is the proof to the claim. So in the next step, we'll focus on the right triangle ODC. In the right triangle ODC, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle, that is this angle, must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. Likewise, we focus on the right triangle PQC. On the right triangle PQC, this angle equals to theta. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. And we'll prove that this small right triangle is similar to the big right triangle. So we prove that the big right triangle PQC is similar to the small right green triangle, triangle ODC. Okay. So why those two triangles are similar to each other? First of all, let's right now found out that those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So here, angle QPC is equal to this angle, that is actually angle DOC, repeat again, angle QPC equals to angle DOC, they are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. So you can write down that angle PQC, this angle, is equal to this angle, that is actually angle ODC, angle PQC equals to angle ODC, they are both equal to 90 degrees, therefore they are equal to each other. Finally, this angle theta, is a common angle that belongs to both triangles, so angle theta equals to itself. Or we can name angle theta and angle as angle PCQ. That is equal to itself. We can name angle theta also as angle OCD. Angle OCD. Repeat again. This equation states that angle theta equals to itself. Okay, so actually we found out that triangle PQC is similar to triangle ODC according to angle similarity rule. I write it down. Triangle PQC is similar. This is the sign of similar to triangle ODC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PQ in the right big triangle over OD in the small right green triangle is equal to QC in the big right triangle, QC over DC. And again, we conclude that PQ or D is equal to QC over DC. Okay. PQ equals to R, it is the radius of the big circle, over OD equals to 1 unit, it is the radius of the small circle, and it is equal to QC. What is the value of QC? The value of QC equals to 3 plus 1 plus, here it is 3 plus 1, and you know that each side of the square is equal to 3 units, so it is 3 plus 1 plus 3, that is 7, plus HQ. 7 plus HQ over DC. Here, DC equals to 3 units. So, in conclusion, we found that according to equation number 1, R equals to 7 plus HQ over 3. Here we multiply this equation number 1 by 3, and we'll get that according to equation number 1, 3R equals to 7 plus HQ. So here we subtract 7 from this equation number 1, and we get that according to equation number 1, 3R minus 7 equals to HQ. Okay, so we actually found out that 3R minus 7 equals to HQ, so we can write in the drawing that HQ equals to 3R minus 7 So here we have 3 possibilities for the value of the radius of the big circle, the radius that we are looking for. The first possibility is that the radius is less than 3 units. The second possibility is the radius is equal to 3 units exactly. And the first possibility is that the radius is greater than 3 units. So we examine each case. So in the first case, we assume that the radius capital R is less than 3 units. Okay. Repeat again. Assume that the radius of the big circle is less than 3 units. If the radius is less than 3 units, the radius can be equal to either 1 or 2 units. So if R equals to 2, then from equation number 1, that HQ equals to 3R minus 7. We know that R equals to 2, so we can substitute R by 2, and we get that HQ equals to 3R, and R is 2, so 3 times 2 is 6, minus 7. 6 minus 7 is minus 1. So we found out that HQ equals to minus 1. But because of the fact that HQ is the length of this line segment, HQ as a length must be a positive number. It can never be equal to minus 1. So R can never be equal to 2. So we'll examine the possibility that R equals to 1. So if R equals to 1, then again we'll put the value of R inside equation number 1. According to equation number 1, h cubed is equals to 3R minus 7 and R equals to 1. So here, if R equals to 1, so 3R is 3 times 1 is 3 minus 7. 3 minus 7 is minus 4. So again, if I know that h cubed is equal to minus 4, that is a negative number, and again we can write down that h cubed is a length, and as a length it must be a positive number. Okay. So in conclusion, we can summarize and say that R cannot be less than 3 units. So it cannot equal to 1, and it also cannot be equal to 2. So we'll examine the second case, that R is exactly equals to 3 units. If R equals to 3 units, then we have a radius that is equal to 3 units. So here R equals to 3, and we also know that one side of square is also equals to 3 units according to what is given as the question. So here we'll get R equals to 3. So here the radius is drawn to the point of tendency. Therefore this angle equals to 90 degrees. Again we have the square that is also equals to 3 units. Each side equals to 3 units. Okay, according to rule number 1, here the radius is drawn to the point of tendency, therefore this angle equals to 90 degrees and this angle also equals to 90 degrees. So here PQ, the center is P, this point, the point of tendency is Q. So inside quadrilateral, this point is point G. So inside quadrilateral PGQ, PGQH, inside this quadrilateral we have 1, 2, 3 right angles. Again, inside this quadrilateral we have 1, 2, 3 right angles. So therefore the fourth angle must be also equal to 90 degrees. So actually quadrilateral PGQH has 4 right angles. Therefore we relate to quadrilateral PGQH is a rectangle. Why? Because it has 4 right angles. For the other one, PG or PQGH is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. Okay? So the opposite sides of a rectangle PQGH are equal to each other. That is to say, PG equals to QH. PG is equal to QH. But PG equals to 3 units, it is the radius of the circle according to our assumption. And from this equation, 3 equals to PG equals to QH, we derive that QH is also equals to 3 units. QH equals to 3 units. Therefore, we actually found out that quadrilateral PGQH is not a rectangle but a square, because all of its sides are equal to each other. So we have already found out that QH is equal to 3R minus 7 from one side, but from the other side it is equal to 3. So from this equation 3 equals to QH equals to 3R minus 7, we will derive that 3 equals to 3R minus 7. Here we add 7 to this equation and we get that 3R is equal to 3 plus 7, that is 10. We divide this equation by 3 and we get that R equals to 3.333 or 3.333 from one side, but according to our assumption R equals to 3. So here we have a contradiction. R cannot be equal simultaneously to 3 and 3.333. Therefore, due to the contradiction, we derive that R cannot be equal to 3 units. And we'll examine the third case, that R is greater than 3. If R is greater than 3 units, it is the third case. Then we have a radius that is greater than 3, therefore the square is equal to 3 units, so the radius will be greater than 3. This is the radius of the big circle that is greater than 3. Here from point G we draw perpendicular on the radius PQ. Repeat again. From point G we draw perpendicular on the radius PQ. So here this angle equals to 90 degrees, and this angle it is also equal to 90 degrees. According to our construction, we define the touching point of the perpendicular from point G and PQ as T. We join points P and G together by a straight line. So here, point P is the center of the circle, point G is the point of the circle itself, therefore PG is the radius of the circle, that is equal to R. Inside quadrilateral TQHG, we have 1, 2, 3 right angles. Again, inside quadrilateral TGQH, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So this quadrilateral that has four angles, 4 right angles, and relate it as a rectangle. So we write down that quadrilateral PGQH is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, GH equals to TQ. GH equals to TQ. But QH equals, here, GH equals to TQ is, GH equals to TQ, but here GH equals to 3 units. It is one side of the square. So GH equals to 3. So from this equation, 3 equals to GH equals to TQ. We will derive that TQ is also equals to 3 units. Here TQ equals to 3 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that QH is equal to TG. Here, QH equals to TG. According to the rule that the opposite sides of a rectangle are equal to each other. But we have already found out that QH equals to 3R minus 7. So I can write here that QH equals to 3R minus 7. And for this equation, 3R minus 7 equals to QH equals to TG, we derive that TG is also equals to 3R minus 7. TG is equals to 3R minus 7. And what is the value of TP? It is very easy to see from the drawing that TP is equals to PQ minus TQ. PQ minus TQ equals to TP. So TP equals to PQ, that is the radius of the circle that is equal to capital R, minus TQ. And we only found out that TQ equals to 3. So in conclusion, we found out that TP equals to R minus 3. So I write it here that TP equals to capital R minus 3. So in the next step, we will implement the Pythagoras theorem on the right green triangle, triangle TPG. On the right big triangle, triangle TPG. According to the Pythagoras theorem, in the right green triangle, triangle PTG. In the right green triangle, triangle PTG. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PG, therefore the square of the hypotenuse is PG square. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to T square plus Tg square. Repeat again. According to the Pythagoras theorem, we found out that Pg square equals to Pt square plus Td square. So here PG is the radius of the circle that is equal to R, and is equal to Pt square. Pt is R minus 3, so Pt square is R minus 3 square. Plus Tg square. Here Tg equals to 3r minus 7, therefore Tg square is 3r minus 7 square. Okay, so in conclusion, we found out that according to the Pythagoras theorem, r square equals to r minus 3 square plus 3r minus 7 square. We'll open the brackets in this side of equation number 1, and we get that according to equation number 1, r square is equal to r minus 3 square. R minus 3 square is r square plus 3 square, that is 9, minus 2 times r times 3 is minus 6r, plus 3r minus 7 is equal to 3r squared, that is 9r square, again 3r minus 7 square is equals to 9r square plus 7 square, that is 49, minus 2 times 3 is 6, and 6 times minus 7 is minus 42. So in conclusion, it is minus 42r. So here we have r square on both sides of the equation, so r square will get cancelled. So in this side of the equation we have 0, that is equal to 9r square minus 6 square minus 42 square is minus 48 square plus 49 plus 9 is 58. So in conclusion, found out that (9r square minus 40r plus 58 equals to 0. So this is the quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus C equals to 0. Here A, B and C are the coefficient of the quadratic equation, and X is the variable that we are looking for, and we find out the value of X according to a special formula for X. X is equals to minus B plus minus square root of B squared minus 4 times AC over 2A. Okay. So in our specific quadratic equation, A equals to 9, the coefficient A equals to 9, the coefficient B equals to minus 48, and the coefficient C equals to 58. And the variable that we are looking for is R, so X equals to R. So we put the data inside the equation for X, and we find out the values of R because X equals to R. So we get that R equals to minus B, B equals to minus 48, so minus B is minus 48, that is 48, plus minus square root of, square root of 48 square is 2304 minus 4 times 9 is minus 36, and minus 36 times 58 is 288. Over 18, of course, because A is 9, so 2 times 9 is 18. So R equals to 48 plus minus 2304 minus 2088 is 216. 18. Okay, all divided by 18. So here R equals to 48 plus minus, and the square root of 216 is 14.6969 over 18. So here we have two possibilities for the solution for R. The first possibility is that R is equal to 48 minus 14.6969 over 18. 48 minus 14.69 is 33.031 over 18. It is equal to 0.85. So we found out that R equals to 0.85 units, and it is not possible because R must be greater than 3 units, as we already found out. So only the second possibility is left, that R is equal to 48 plus 14.69 over 18. Here we get that the radius of the circle it is equal to 3.48 per units. Okay. So finished with the question. The next step I'll summarize the lecture. So in the drawing we have 2 circles and also a square that is inside the big circle and the big triangle. You know that the radius of the square and the one side of the square is equal to 3 units, and the radius of the small circle is equal to 1 unit. And our mission is to find out the radius of the big circle. So actually, in this question, we use mainly 3 rules. The first rule states that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here, the radius OM is drawn to the point of tendency, therefore according to rule number 1, this angle equals 90 degrees, and this angle will be also equal to 90 degrees. Okay, then we use also rule number 2. According to rule number 2, the lengths of 2 tangents from a common external point to a circle are equal. So we have the common external point P, for the common external point P, we have 2 tangents to the circle. Tangent PA and tangent PB, and according to rule number 2, they are equal to each other. And then presented to you rule number 3. And according to rule number 3, the sum of the angles on one side of a straight line is equal to 360 degrees. Okay, those are the 3 rules that we use to solve this question. Then we focused on the green triangle FEC, on the green triangle FEC according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay, so the hypotenuse is EC, therefore the square of the hypotenuse is EC square, and it is equal to FE square plus, it is actually the hypotenuse is FC, so it is FC square that is equal to FE square plus E square. Here in the right hand triangle FEC. FC square equals to FE square plus EC square. Here FC equals to time plus x, 2 plus x, therefore AC square is 2 plus x square. FE equals to 3, so FE square is 3 squared, that is 9. And ED equals to 1 plus x, here 1 plus x, therefore EC square equals to 1 plus x square. So 2 plus x square equals to 2 squared, that is 4 plus x square, plus 2 times 2x, that is 4x, and it is equal to 1 plus x square, that is to say it is equal to 9 plus 1 square, and that is 1 minus 2x. So here we have x square on both sides of the equation, so x square will get cancelled. In this side of the equation, we have 4 plus 4x, and the other side of the equation we have 9 plus 1, that is 10, plus 2x. Here we subtracted 4 from this equation, equation number 1, and found out that 4x equals to 10 minus 6 is 10 minus 4 is 6. So we have 4x that is equal to 6 plus 2x. We subtracted 2x from this equation and found out that 4x minus 2x is 2x, and 2x equals to 6. Then we divided this equation number 1 by 2, and we found out that x equals to 3. So here x equals to 3, x equals to 3. Then we proved that those two right triangles can go into each other. Why they can go into each other? First of all, we know that side CS equals to side CD equals to 3 units according to rule number 2. In addition, we know that SO equals to OD equals to 1. They are both the radii of the circle, that is equal to 1. And finally, we have side CO, that is the common side, it belongs to both triangles, so CO equals to itself. So we actually found out that those two right triangles can go into each other according to side rule. Then we join points S and D together by straight line, and we found out that CO, actually here, before that, from the fact that those two triangles can go into each other, we derived that those two angles must be equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So those two triangles are congruent, therefore those two corresponding angles must be also equal to each other. So if one angle is theta, then the other angle is also theta. Then actually found out that CO is the angle bisector of angle C in triangle SDC. Again, OC is the angle bisector of angle C in triangle SDC. Okay. Then we joined points P and then together by straight line. Point P is the center of the circle, point N is the point of the circle itself, therefore Pn is the radius of the circle, that is equal to R. We joined points P and C together by straight line. In this way, we created those two right triangles, and we proved that those two right triangles can meet to each other according to side rule. So why those two triangles can go into each other? First of all, if we focus on the common external point, point C, for the common external point C, we have two tangents to the circle. Tangent CN and tangent CQ, and those two tangents must be equal to each other according to rule number 2. In addition, we have NP equals to PQ, they are both the radii of the circle, therefore they are equal to each other. And finally, we have PC that is equal to itself. Okay? So it's a common side that belongs to both triangles. So we actually proved that the two big triangles can go into each other according to side rule. And then actually also know that PC But before that, from the fact that those two triangles can point to each other, we derive that those two angles must be equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one angle is equal to alpha, to theta, then the other angle must be also equal to theta, because they are equal to each other. So we actually found out that angle bisector PC bisect angle C, PC angle bisector AC of triangle NQC. This triangle NQC. PC is the angle bisector of C, and we also found out that OC is also angle bisector of the same angle C. Then we claimed that CO, the angle bisector CO, must pass for point P. Again, the angle bisector CO must pass for point C. Okay, here I take again. Our claim is that CO passes for point P. That is to say, point C, O, and P, they are all located on the same straight line. And we proved in the negative way. In a negative way, we assumed that CO doesn't pass for point P. Here, CO doesn't pass for point P. So if CO doesn't pass for point P, then we have here two angles OCD that is equal to theta, here angle OCD that is equal to theta, and the second angle PCD, PCB can never be equal to theta. Why? I'll explain why. Because here BC and DC, they're both located on the same straight line. So you can say that we have one leg of those two angles that are a common leg, while the second leg is PC and OC. But because of the fact that OC doesn't pass for point C, that is to say COP are not located on the same straight line, therefore CO and CP are two different straight lines. Okay, here CP and CO must be two different straight lines. Why? Because point CO and P, they are all not located on the same straight line. That is to say, CO and CP, they are two different straight lines. Therefore, if we have one leg of an angle that is a common leg, and the second leg is not on the same straight line of the other leg, it means that those two angles must be different angles. In order that the two angles will be equal to each other, if one leg is on the same straight line, then the other leg must be also on the same straight line. But according to our assumption, the second leg of this angle is not located on the same straight line of the second leg of this angle. Therefore, PC and OC, they are two different straight lines. That is to say, those two angles can never be equal to each other. So if this angle is theta, this angle must be equal to other angle alpha, that is not equal to theta. Okay, because we have one leg that is a common leg, and the other leg, it is not a common leg, because the other leg is not located on the same straight line. Why? Because points C, O, and P, they are not on the same straight line according to our assumption. Therefore, we created here two different angles. This is angle theta and this is angle alpha. Therefore, we have here actually two angle bisectors that bisects the same angle, angle C, into two different halves. The angle bisector CO bisects angle C into two halves, and each half equals to theta. While angle bisector CP bisects the same angle, angle C, into two different halves, and each half equals to alpha. And it is impossible that one angle will be bisected into two different halves. For example, if angle C equals to 30 degrees, then any angle bisector will bisect angle theta into two halves, that each half equals to 15 degrees and 15 degrees, and not anymore. Okay? So this is a contradiction, that angle theta has two, angle C has two angle bisectors that bisect it into two different halves. And so, because of the assumption that CO doesn't pass from point P, we arrive to a contradiction. So in order to avoid the contradiction, we must conclude that our assumption is not true, and therefore OC passes through point P. Okay? So in the next step, we defined angle DOC. Actually, in triangle DOC, this angle equals to theta. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. Likewise, exactly from the same reason, if we focus on the big right triangle PQC, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Then we proved that the big right triangle PQC is similar to the small right triangle ODC. So while this triangle is going to the green triangle, first of all, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, angle theta is a common angle that belongs to both triangles, so angle theta equals to itself. So we proved that those two triangles are similar to each other according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that PQ over OD is equal to QC over DC. Repeat again. We derive that PQ over OD equals to QC over DC. Okay, PQ equals to R, OD equals to 1, it is the radius of the small circle. QC equals to 3 plus 3 plus 1, that is 7 plus HQ, 7 plus HQ, and DC equals to 3. So according to equation number 1, we found out that R equals to 7 plus HQ over 3. We multiplied this equation by 3 and we found out that 3R equals to 7 plus HQ. We subtracted 7 from this equation and found out that HQ equals to 3R minus 7. So according to equation number 1, HQ equals to 3R minus 7. In the next step, we actually note that R, the radius that we are looking for, could be equal to, could be either less than 3 units. The second case is that R also can be equal to 3 units, and R, the third case is that R is greater than 3 units. So we'll examine each case and we'll find out which is the correct case for our drawing, our question. So we'll assume that R is less than 3 units. If R is less than 3 units, R is a length, so it could be equal to either to 1 unit or 2 units. So if R equals to 2, then we have the equation number 1 that HP equals to 3R minus 7, and if R equals to 2, we will substitute R by 2, 3R. So here we have 3R minus 7, so, and R equals to 2, so 3 R is 3 times 2, that is 6, and 6 minus 7 is minus 1. So we found out that HP is a negative, as a negative number, but HQ is a negative, but HQ is a length, and as a length it must be a positive. So this is not good possibility, and the other possibility is that R equals to 1. Again, we substitute R by 1 in this equation, equation number 1. So HQ equals to 3R minus 7 and R equals to 1. So 3R is 3 times 1. That is to say it is 3. So in conclusion, HQ equals to 3 minus 7. That is minus 4. Again, HQ is a length, and it can never be equal to a negative number. Therefore, we cancel this solution. So in conclusion, we found out that R cannot be less than 3 units. Then we have the second case that R is equal to exactly 3 units. So if R is equal to exactly to 3 units, then we have here a radius that is equal to 3 units, and the one side of the sphere is also equal to 3 units. Okay? So here we have here actually a rectangle. Why? Because we got here 1, 2, 3 rectangles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrilateral PGQH, this quadrilateral is a rectangle because it has 4 rectangles. And you know that the opposite sides of a rectangle are equal to each other. That is to say, PG equals to QH. PG equals to QH. But PG is the radius of the circle that is equal to 3 units according to our assumption. And from this equation, P equals to PG equals to HQ, we derive that HQ is also equals to 3. So from one side, HQ equals to 3 units. But from the other side, we have already found out that HQ equals to 3R minus 7. From this equation, 3 equals to QH equals to 3R minus 7. We derive that 3 equals to 3R minus 7. Here, we will add 7 to this equation, and we get that 3R equals to 10. We divide this equation by 3, and we get that R equals to 3.333. And according to our assumption, R equals to 3. And this is a contradiction. R cannot be equal both to 3 and 3.333. So due to the contradiction, we cancel this solution. So R cannot be equal to 3. So the only possibility that is left, that is R is greater than 3 units. So if R is greater than 3 units, then we will have here this circle. R is greater than 3, therefore this square is equal to 3. So all the sides are equal to 3. And again, we have here a rectangle, because it has quadrangle TGQH as 4 right angles, therefore it is a rectangle, and the opposite sides of a rectangle are equal to each other. That is to say, GH equals to TP. GH equals to TP. But TP is the radius of the circle. No, but before that, actually, from point G, we go perpendicular on the radius PQ. Therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Therefore, in quadrangle GTPQ, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrangle TGQH has 4 right angles. Therefore, quadrangle TGQH is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, TQ equals to GH. TQ equals to GH. But TQ is it is equal to 3. Actually, GH equals to 3 because it is one side of a square that is equal to 3 units. And from this equation, 3 equals to GH equals to TQ, we will derive that TQ is also equals to 3 units. Likewise, according to the rule that the opposite sides of a rectangle are equal to each other, we get that TG is equal to QH. TG equals to QH. But we have already found out that QH equals to 3R minus 7. So from this equation, 3R minus 7 equals to QH equals to TG, we will derive that TG is also equals to 3R minus 7. Here, TG is also equals to 3R minus 7. And what is the value of TP? From the domain, it is very easy to see that TP equals to PQ minus TQ. Again, PQ minus TQ equals to PT. So PT or TP equals to PQ minus TQ. So TP equals to PQ, that is R, minus PQ, that is 3. So in conclusion, found out that TP equals to R minus 3. Then we implemented the Pythagoras theorem on the right green triangle, triangle PTH. Here point P is the center of the circle, point G is the point of the circle Z, therefore PG is the radius of the circle. We implemented the Pythagoras theorem on this right triangle, triangle PTG. The square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say PG square equals to PT square plus TG square. Let's see it again. In the right green triangle, triangle PTG, PG square equals to TP, PT square plus TG square. PG is the radius, so PG square is R square. PT equals to R minus 3, therefore PT square is R minus 3 square plus TG square. TG square equals to 3R minus 7, so therefore TG square is 4R minus 7 square. We open the brackets on this side of the equation and found out that R square equals to R minus 3 square. R minus 3 square equals to R square plus 3 square, that is 9, minus 2 times R times 3, that is minus 6R, plus 3R minus 7 square. 3R minus 7 square equals to 3R square, that is 9R square, plus 7 square, that is 49, minus 2 times